Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. We will talk little bit on numerical methods, differential equations, predominantly ordinary differential equations. I am not going to spend too much time on these numerical methods because that itself can be a separate course on its own, but we will come across numerical methods in drug discovery because like I mentioned, if you are looking at minima, if you are going to look at minima, then we need to think that dy by dx should be equal to 0 and d square y by dx square should be greater than 0. So, dy by dx is calculated, okay, which we looked at in the previous class. Okay. So, we need to understand how the computers use numerical techniques to calculate that. If it is an analytical solution, then it is quite simple. For example, if we have y is equal to x square, so dy by dx is equal to 2x, we must have studied in our school. Okay. But then imagine a function which has got very complicated independent variables in the numerator and the denominator. So, it is not possible to do analytically, and for computers they have to calculate these dy by dx okay, using numerical techniques. So, like in our force field method, we have the distance or the bond length, bond angle, bond torsion. So, we have 3 independent variables which needs to be okay, adjusted so that the total energy which is on the left hand side becomes the minimum. So, we will have many df by dx, df by dy, df by dz to be calculated. So, if it is analytical, as I said, it is easy, like y is equal to x square means we can calculate dy by dx is equal to 2x. Otherwise, we need to do it numerically. So, estimating the derivative of a mathematical function, that is called finite different approximation. So, the simplest one is a 2-point estimation to compute the slope at the point. Dy by dx, as you know, is approximated to delta y by delta x, okay, which is equal to yx plus h minus yx divided by h. Actually, this is it will come out like that. So, h is the small distance. So, you estimate the function y at x plus h, then you estimate the function at yx. So, you take the difference, divide by h here, as you can see here. So, if this is your function going like that, okay. So, I want to calculate the slope at this place. So, the approximation here is you calculate the function at point x, you calculate the function at x plus h, and then you take the difference, divide by h. Actually, that is the slope, this distance divided by this distance, that is the approximated to the slope here. As you can see, if h is smaller and smaller, this becomes the exact slope, but if x is larger and larger, you see the difference here. Okay. So, that is the error that comes in. So, we need to keep a very small h so that we get a very good approximation for dy by dx at this point x, okay, at this point x. Okay. But if you are going to keep a very small h, you are going to do too much of computation. So, the computational effort also increases. So, this is the simplest method. So, there are more slightly more involved method which does not require too much calculation, but still can get a better approximation of the slope here. Okay. So, as you can see here, you are approximating the slope at this place, okay, by taking the function at x plus h and calculating the function at fx, subtracting and then dividing by the distance h. Okay. This is called the finite difference method. This is called the forward method. There is also a backward method, but this is called the forward method. So, like I said, if you have the analytical solution possible, then it is most accurate, otherwise in most of the cases it is not possible to have analytical solution. So, we use the numerical method for estimating the dy by dx. Okay. There is another method that is called centered difference formula. That means you do x plus h, x minus h, and then divide by 2h. Okay. So, this is x plus h, and then we have the x plus h here, we have the x here, and suppose you have x minus h here. Okay. So, you calculate at x minus h. So, this difference will be 2h. Okay. So, this is at a function of x h, and this is at a function at x minus h, and this difference is 2h. So, you do the same calculation, dy by dx is equal to y at x plus h minus y at x minus h divided by 2h. This is called the center difference. This is slightly more accurate than the forward difference, whereas in the forward difference we take this point and this point values, subtract by, take the difference, divide by h, whereas in the center difference we take here and then divide by 2h. Okay. So, this is like taking an average. Then there are higher order methods, like I said, these methods, like I showed you, the forward difference, center difference, have error of the order of h square. So, if h is small, error will be corresponding to x square. So, if I divide h 1/10, then error also will become 1/100th of that. Higher order methods, there is one method which is called a 5-point method, as you can see here. Okay, this is called a 5-point method. Okay. So, you calculate the function at 2h, minus 2h, h and minus h, and then you use this formula and then divide by 12h to calculate the derivative, first derivative. Okay. So, you calculate the function at 2h, minus 2h, then again h, minus h, okay, and then this has an error of the order of h power 4. Okay, this has an order of h power 4. Okay, so there is another method that is called the backward difference method. So, just like we take in the first case x plus h and x minus h, we take x and x minus h. Okay. So, this is called a backward difference method. As you can see here, we take x plus h and x, here we take x and x minus h. So, that is why this is called a backward difference method. Okay. This also has the error of the order of h square, just like the forward difference method. Okay. So, all these methods have errors in the order of h square, and this higher order methods where 5-point method has an error order of h power 4. So, softwares generally use higher order methods, and instead of reducing the size of h, higher order methods can be more accurate and give very good estimation of the error values. Okay. So, let us look at this. For example, okay, for example, I have y is equal to x square, dy by dx is equal to 2x. Okay. So, suppose I want to find out at x is equal to 5. Okay, what do I do is in the forward method, what will I do? In the forward method, I will calculate y at x plus h. Suppose I take h is equal to 0.01. Okay, if I take x is equal to 0.01 at 5, y is equal to x square. So, we can do it as a okay. So, this is at x plus h, because it is x square, we calculate a8 plus b1, that is your h, and this is at xh. So, that is equal to 8 raised to the power 2. Okay. Then what do we do is we take a difference. the difference is this minus this is the difference, and then the divided by h. Okay, so it comes to 10.01, but whereas if you take y is equal to x square, okay, and dy by dx is equal to 2x. So at x is equal to 5, the answer will come out to be 10, that is the exact value. This is the exact value. Okay, this is numerical differentiation. Do you understand this? Okay, this is the exact value because at 5 dy by dx is equal to 2x, so I put 2 into 5, that comes to 10. Okay, if I do numerical differentiation, what do? I will take the y value at 5 plus 0.01 minus y value at 5 and then divided by h. Here I have taken h as 0.01. So y at 5 plus 0.01 is 25.10001. Y at 5 is equal to 25, take the difference here and then I divide by the h, that is 0.01. So numerical differentiation gives me 10.01 whereas the exact is 10. So you see there is a small error of 0.01. If I increase the if I increase the step length, .02, it's become 10.02, the error has increased. So if I increase it to 0.1 for example, so the error has become, see, as you can see the numerical differentiation gives 10.1 whereas the exact value does not change, it is 10. So you can see the numerical gives almost 10% error. Okay. So if I put a 0, 1, you get 1% error. So if the step length is 0.01 I get 1% error, if the step length is 0.1 I get 10% error. So if I make it still smaller, okay, I get almost 0.1% error. So depending upon the step length the error keeps coming down, okay, as you can see. So if I keep 0.01 I get 1% error, 0.1 I get 10% error, 0.001 it gets 0.1% error, okay, for this type of function y is equal to x square. So because x square it's going to rise in a quadratic fashion, so the dy by dx can change dramatically. Okay. Again it will not be constant all the time because if I take say at x is equal to 10 I want to find out. Okay, so it can change depending upon which point I am trying to estimate the dy by dx. So as you can see the error depends upon the step length h. Okay, you can have 1% error, you can have 10% error. Larger the step length you can differentiate things faster, so the computational time is less, but the error will keep adding and adding and adding, which is very dangerous. Smaller the step length the error will be very less, but you are going to have more computational. See, this is error is only 0.1%, even that could be higher. Okay, so ideally I may go into 0.0005. Okay, so the error is 0.05%. Okay, so maybe that is okay, or 0.0001. Okay, so the error is okay 0.01%. So but look at the step length, so 0.301. So if I want to calculate dy by dx over a distance of 0 to 10, that means for example if I want to calculate a distance of 0 to 10 then number of calculations will be almost 100,000, 1 lakh. So a lot of calculations. Okay. So if the step length is very small, the number of calculations will also increase. Okay. But if step length is small, your error also will be less. For example, if you look at this 0.0001, my error is 0.01% in my different dy by dx, whereas if I go to 0.01, my error becomes 1%, which is too much. We have to have about 0.1% error is very good to have, but your step length also will keep I mean number of calculations also keep increasing. So that is the main I mean point which you need to note when you are doing numerical differentiation, or for example even numerical integration. The step length determines the error, and the step length also determines the number of calculations we have to do. So there are methods which use reasonably small or reasonably big step length, but more accurate calculations. For example, if you look at the 5-point method for the first derivative, okay, where it uses x plus 2h plus this and so on. So the y is calculated at 5 different places. Okay. So the error they say is in the order of h power 4. Okay. We can try that also, 0.01 as it says. Okay. So we say 5, it is calculated as x plus 2h. So it is x square is your problem. So we can calculate plus 2 into h. Okay. Then you calculate at x plus h, that is open bracket x plus so we have at x plus 2h, then x plus h, then x minus h, x minus h, then x minus 2h, minus 2 into so this comes to equal to minus this plus 8 into plus this minus 8 into plus this plus this divided by open bracket 12 into square coming into all these places which I missed out. Yeah, see, I missed out that square term, that is why. Okay, so you calculate at x plus 2h, then you calculate x plus h, then you calculate x minus h, then you calculate x minus 2h. Okay, then you use this formula x plus 2h, that is minus of plus 8 into x plus h minus 8 into x minus h y into minus 2h divided by 12h. So we got 10, whereas if you use a simple forward differential, the simple method, you get 10.01, whereas the 5-point method gives you 10, as which is exactly matching with your answer. Okay, so if I make it as a 0.1, for example if I make the step length very large, Okay. As you can see again the simple method gives you simple 2-point method gives error 10% error, whereas the 5-point method is still very good. Okay. So, you still get very good answer with the 5-point method when compared to the 1-point method. Okay. So, the very good step lengths can be included, okay, with respect to the 5-point method. That is the beauty of this type of method. So, we can improve on the error, but at the same time have a reasonably large h value, the step length, so that we get a reasonably good dy by dx. So, this numerical differentiation is very important, which is the backbone in many of the conformational search algorithms. When you start with the original conformation and then you want to reach the conformation so that the energy is minimum. So, in order to achieve that, like I said, the dy by dx has to be so dy by dx has to be equal to 0 and d square y by dx square has to be greater than 0. So, in order to calculate this dy by dx is equal to 0, many differential equations have to be arrived at. So, generally if the numerical methods are followed, where you use this type of, this is a first order 2-point estimation, dy by dx is equal to y at x plus h minus y at x divided by h, okay, divided by h, and you have the center difference, that means you find out from x plus h and x minus h divided by 2h, or we have a 5-point method which we follow, that means we take at x plus 2h, x plus h, x minus h, x minus 2h, and then divide by 12h. Okay, the errors are very little here in this type of method, or there is a backward difference, but again this also has the error of the order of h square. Okay. So, as I showed you that the 5-point method like are always good, which are better approximation of the difference, getting the differentiation done using numerical, okay, maintaining your h reasonably large. Okay, these are needed for getting the confirmation of minimum energy confirmation, okay, where we use this type of dy by dx is equal to 0 requirement. Okay. So, similarly we also have a numerical integration also. Okay. For example, if dy by dx is equal to y square, analytically what do? We take this here, take that here, dy by y square is equal to dx, integrating both sides, minus 1 by y is equal to x plus constant. Okay. So, this we must have done in our okay, final year school or even in your engineering first year and so on actually. Okay. So, if it is an analytical, so life is easy, but then if you have very complicated equation here, okay, then that is not possible. So, you may have dy by dx is equal to even function of x and y, very complicated equation. Then we have to solve this numerically only, and there are many methods, numerical methods that are available which does this type of calculation. Okay. So, we want to find out y at different points at point n plus h, n plus 2h, n plus 3h, like that we need to, this is known as a numerical integration. So, there are many methods, simple and very difficult methods. For example, the easiest one is called the Euler's forward method. So, I know the value of y at xn, okay, I know the value of y, or I know yn at xn, okay, like this one I know. Now, I want to find out at xn plus 1 what is the value of y, that is the question I am trying to find out. So, there are many methods are there, and the simplest is the Euler's forward method. So, what do? That is whatever we did numerical differentiation, here we are doing the numerical integration. So, we take h here, again h is the distance or the step length, okay, we calculate the function at xn yn here, okay, we calculate the function at this place, okay, at this place, and then we get the f of xn yn, okay, then that is the slope like here, and then multiply by h, and then we say that is yn plus 1, okay. This of course straightforward, right. So we have the dy by dx, sorry, dy by dx is equal to f of xy, okay. So what do? We take delta y by delta x is equal to f of xy, okay. So delta y is nothing but yn plus 1 minus yn plus 1, and delta x can be h f of xn into yn. So yn plus 1 is equal to yn plus h into f of xn yn. This is what is here given here, understand. So we start from this approximation. This is the simplest method. So if I know the y value at xn value, that is I know yn at xn, I want to find out what is yn plus 1 at xn plus 1, okay. This is my step length from xn to xn plus 1, this is my step length. So what do? I calculate the function, that is the slope here, okay, because this function is nothing but the slope here, dy by dx. So this is the reverse of the previous numerical differentiation, and then I multiply by h here, h is my distance here, okay. So I get the yn plus 1. So as again you can see, this is called Euler's method, and again as you can see here, if h is small, I am going to get a nice y value. If the h is very large, I may end up here, whereas the actual value could be here, because if you have a graph like this turning upwards like this, and then you take this as a linear, obviously there is a difference. That so h has to be small. So either I can put small h, or I can use different methods. There are some very good method, even with large h it can give a very good approximation for yn plus 1, okay, from the slope here, okay. So basically in this method you have the slope here, and then we multiply by the h here, and then add it with xn to get the yn plus 1 value, okay. That is called the Euler's method. Euler's method is the simplest of all these methods. So these two, numerical integration and differentiation, are very important, and we will continue more on this topic. There are simple methods which requires very small h to have very considerably low error value, whereas there are other higher order methods which can also take in larger h, but still the errors can be smaller, like I showed you in the numerical differentiation. Here again when we do numerical integration also, as you can see, if the h is large, with the Euler's method you can have so much error coming into picture, but there are other methods which can address this type of problem in a better way. So we will continue more on these numerical techniques in the next class also, but as I said, numerical methods is a big course of its own. I cannot cover the entire, so I am just going to have only a very fast brief introduction to this particular topic for you, okay. So we will continue more on this. Thank you very much.